Section 250.55 of the National Electrical Code, or NEC, mandates the bonding of metal reinforcing bars, or rebar, in concrete footings and foundations. This section states that the metal reinforcing bars in concrete footings and foundations shall be bonded together into any metal water piping system within 5 feet, or 1.5 meters, with wiring not smaller than number 6 American wire gauge, or AUG, copper or equivalent. The primary purpose of this requirement is to ensure that all metal components within the footing are at the same electrical potential. This equipotential bonding helps prevent corrosion and the formation of stray currents, thereby enhancing the longevity and safety of the structure's electrical system. In commercial buildings, it's crucial that the electrical contractor adheres to the grounding system specifications detailed in the plans. This includes connecting the grounding system to the rebar in the footing, as well as to all other grounding electrodes specified in the design. The fact that a local building inspector might permit deviations from this standard does not negate the NEC requirements. Such allowances do not make the non-compliant practice acceptable or safe. The assertion that connections to rebar and building steel are optional is a misinterpretation of the NEC. Section 250.50 clearly stipulates that all grounding electrodes present at the installation site must be connected to form a comprehensive grounding system. This requirement underscores the importance of utilizing all available grounding means to achieve the lowest possible ground resistance. The ground fault current calculation, where 277 volts to ground and a 25 ohms resistance yields 11 amps, is insufficient to trip a standard 20 amp circuit breaker. However, the adequacy of a grounding system cannot be solely determined by this calculation. The grounding system's primary role is to provide a low impedance path for fault currents. This low impedance path helps ensure that protective devices, such as circuit breakers, operate quickly to clear the fault. This quick fault clearing minimizes the risk of electrical shock and equipment damage. A single ground rod exhibiting a resistance of 25 ohms may not offer a sufficiently low impedance path for fault currents, which can create a hazardous condition. A properly installed grounding system significantly reduces this resistance, enhancing safety. The NEC mandates a multifaceted approach to grounding, utilizing various grounding electrodes to achieve a low resistance path to earth. This approach typically involves connecting to the rebar in the footings, the building steel, a metal water pipe, and supplemental grounding electrodes like ground rods or ground plates. The goal is to create a robust, redundant grounding system that ensures safety and reliability. Considering the specifics of the commercial building scenario, the correct procedure involves firstly ensuring the rebar within the concrete footings and foundations are bonded together using number 6 AWG copper or equivalent. Secondly, connecting this rebar network to any metal water piping system within 5 feet, again using number 6 AWG copper or equivalent. Thirdly, bonding the rebar network to the building steel, ensuring that all structural metal components are integrated into the grounding system. Fourthly, supplementing these connections with additional grounding electrodes, such as ground rods, to further reduce the overall ground resistance. The comprehensive grounding system should be tested to verify that it meets the requirements outlined in the NEC. The tests typically involve measuring the ground resistance and impedance to ensure they are within acceptable limits. Regular inspections and maintenance are essential to ensure the grounding system remains effective over time. These inspections should include visually checking all connections for corrosion or damage and periodically testing the ground resistance. If the ground resistance increases, additional grounding electrodes may be necessary to bring it back within acceptable limits. The grounding system design must take into account the specific characteristics of the installation site. Factors such as soil resistivity, the presence of underground utilities, and the size and type of building all influence the design of the grounding system. A qualified electrical engineer or contractor should perform a thorough site assessment to determine the optimal grounding solution. Proper grounding is essential for electrical safety and equipment protection. By following the guidelines outlined in the NEC and utilizing best practices, it is possible to create a grounding system that provides a safe and reliable electrical environment. Remember that grounding is not merely an optional add-on but a fundamental safety requirement that must be taken seriously. For example, consider a large commercial building with multiple tenants and sensitive electronic equipment. A properly designed and installed grounding system is essential to protect this equipment from voltage surges and other electrical disturbances. A poorly grounded building is much more susceptible to damage from lightning strikes or other transient voltage events. The consequences of inadequate grounding can be severe, ranging from equipment failure to electrical fires and even personal injury. Therefore, it is crucial to prioritize grounding in all electrical installations. To further illustrate the importance of grounding, let's consider a scenario where a ground fault occurs in a piece of electrical equipment. If the equipment is properly grounded, the fault current will flow through the grounding system back to the source, tripping a circuit breaker or fuse and energizing the circuit. This rapid energization minimizes the risk of electrical shock and prevents further damage to the equipment. However, if the equipment is not properly grounded, the fault current may find an alternate path to ground, such as through a person who comes into contact with the equipment. This can result in a severe electrical shock or even death. Grounding is also important for preventing the buildup of static electricity. Static electricity can damage sensitive electronic components and cause fires or explosions in certain environments. By grounding equipment and structures, static charges can be safely dissipated, reducing the risk of these hazards. In addition to the NEC, other standards and regulations may apply to grounding systems. These may include local building codes, industry standards, and requirements from insurance companies. It is important to be familiar with all applicable requirements when designing and installing a grounding system. To ensure that a grounding system is properly installed and maintained, it is recommended to use a qualified electrical contractor. A qualified contractor has the knowledge, skills, and experience to design and install a grounding system that meets all applicable requirements and provides a safe and reliable electrical environment. When selecting an electrical contractor, it is important to verify their credentials and experience. Ask for references and check their licensing and insurance. It is also a good idea to get multiple bids to ensure that you are getting a fair price. The cost of a grounding system can vary depending on the size and complexity of the installation. However, the cost of a proper grounding system is small compared to the potential cost of electrical damage. Investing in a proper grounding system is a wise decision that can protect your property, your equipment, and your personnel. In summary, grounding is a critical component of electrical safety and equipment protection. The NEC requires the bonding of rebar in concrete footings and foundations to ensure that all metal components are at the same electrical potential. A properly designed and installed grounding system provides a low impedance path for fault currents, prevents the build-up of static electricity, and protects against voltage surges and other electrical disturbances. By following the guidelines outlined in the NEC and utilizing best practices, it is possible to create a grounding system that provides a safe and reliable electrical environment. Always consult with a qualified electrical contractor to ensure that your grounding system meets all applicable requirements. The grounding electrode system, as covered in NEC Article 250, is fundamental to electrical safety. It establishes a connection to the earth, providing a low impedance path for fault currents, which helps to quickly trip over current protective devices like circuit breakers and fuses. This rapid clearing of faults minimizes the risk of electrical shock and fire hazards. The grounding electrode system typically includes several components working together to achieve a low resistance connection to the earth. These components can include metal underground water pipe, the metal frame of the building or structure, concrete encased electrodes or ground rods and ground rings. The NEC specifies requirements for the size, material, and installation of these electrodes. The metal underground water pipe, if available, is often used as a primary grounding electrode. However, it must be supplemented by an additional electrode to ensure a reliable connection to the earth. The metal frame of the building or structure, if effectively grounded, can also serve as a grounding electrode. This typically involves connecting the building steel to the grounding system using appropriate bonding jumpers. Concrete encased electrodes, often referred to as UFA-grounds, are commonly used in new construction. These electrodes consist of at least 20 feet of bare copper conductor encased in concrete. They provide a very effective grounding connection due to the large surface area in contact with the earth. Round rods are another common type of grounding electrode. They are typically driven into the earth and connected to the grounding system using clamps and conductors. The NEC specifies requirements for the size, material, and spacing of ground rods. A ground ring is a continuous loop of bare copper conductor buried in the earth around the perimeter of a building or structure. It provides a very effective grounding connection, especially in areas with high soil resistivity. The NEC also addresses the bonding of various metal components within a building or structure to the grounding system. Bonding is the process of connecting metal parts together to create an electrically conductive path. This helps to ensure that all metal components are at the same electrical potential, reducing the risk of electrical shock. Bonding is required for metal water pipes, gas pipes, metal conduits, and other metal components that could become energized. The NEC specifies requirements for the size and type of bonding conductors. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods. The NEC also addresses the grounding of electrical equipment. Equipment grounding conductors are used to connect the metal enclosures of electrical equipment to the grounding system. This helps to ensure that the equipment enclosures are at the same electrical potential as the grounding system, reducing the risk of electrical shock. The equipment grounding conductor must be sized according to the overcurrent protection device protecting the circuit. The NEC provides tables that specify the minimum size of the equipment grounding conductor based on the size of the overcurrent protection device. The equipment grounding conductor must be connected to the equipment enclosure using approved methods. Regular inspections and testing of the grounding system are essential to ensure that it is functioning properly. The NEC recommends that grounding systems be inspected and tested periodically. Ground resistance testing is used to measure the resistance of the grounding system to the earth. This test can help to identify problems with the grounding system, such as corroded connections or damaged electrodes. The NEC provides guidelines for acceptable ground resistance values. If the ground resistance is too high, corrective action must be taken to improve the grounding system. This may involve adding additional grounding electrodes or repairing damaged connections. Proper grounding is essential for electrical safety and equipment protection. By following the requirements of the NEC and utilizing best practices, it is possible to create a grounding system that provides a safe and reliable electrical environment. Always consult with a qualified electrical contractor to ensure that your grounding system meets all applicable requirements.